Good evening, everybody. Welcome to Tippett's Physics. What is crappin'? In this video, we're going to look at magnetic field properties. We already discussed stuff in class yesterday. We're just going to expand upon it. So the first thing we want to look at is electric fields. And if we remember from the last unit, if we have a positive and a negative charge, the electric field goes out of the positive and into the negative. And we have something very similar for magnets. Instead of charges, we have poles. And we have the North Pole and the South Pole. And similar to charges, the magnetic field goes out of the north and into the south. So out of the north into the south. If you remember from the electricity unit, we said out of positive into negative. So we used op-in, out of positive into negative. For magnets, we have out of north into south. So on is out of north into south. So these lines that we're looking at for the magnets, these are called magnetic field lines. Magnetic field lines. And what they represent is the strength of the magnetic force. So these are the strength of the magnetic force. I'll say force field surrounding the magnet. Now we can measure how strong the magnet is by looking at the density of the magnetic field lines. So how close together these lines are represent how strong they are. If they're closer together, we have a stronger magnetic field. If they're farther apart, it's weaker. And there's a word for this, that's called the magnetic flux. Magnetic flux. You may have heard this as the flux capacitor in Back to the Future. Not quite related, but same word in terms of flux. So this is the density of the field lines that represent the strength. If we place two magnets together or next to each other of opposite poles, so if we had a south pole and a north pole, the magnetic field lines are also similar to what we'd experience for charges. So they go out of the north into the south. Out of north into south. And then same with here, out of north into south. Sorry, that one should go, top one should be more like this. And then somewhere along the lines, in the back, out of the north, all the way over into the south on the other one. Now one question that's commonly asked is, well, what happens if I break this magnet apart? So if we look at the magnet on the left, and we split it apart down the center, what's going to happen to the magnetic poles? Well, what happens is that the north stays north, and the right side over, and the left one becomes south, and then this one, the right side is still south, and the left side is north. If we split these magnets again in half, we'll now have a north and south, and we'll have a north and south. And same thing with the other one. So you can do this to infinity, and you might ask, well, can I get just a south pole or a north pole? In fact, last year, a monopole was created. That's a magnet with just one field, so just a south or a north pole. Now that had to be done in a laboratory at very, very cold temperatures, so I guess we could say that it is doable, but it's not very practical for the time being. So these magnets that we've been looking at so far, these are ones that you probably play with on a regular basis if you've ever played with magnets. These are called permanent magnets. And they are made out of permanent magnets. And they are magnets that are metals that are already magnetized, and they are composed of iron, nickel, cobalt, and aluminum. So you might ask yourself, well, why is it that some metals are permanent magnets and others could be magnetized but don't keep their magnetism? So we have to go back to chemistry, possibly last year, or maybe you never took it. We have to think about metals and objects themselves. We know that all objects are made out of atoms, and atoms are composed of protons, neutrons, and electrons. What we want to look at are the electrons inside the atom. Electrons have a spin state. Now, they're not actually spinning, so to speak. It's kind of hard to think about it at the microscopic level. But electrons, we say, have either spin up or spin down. Either spin up or spin down. And we looked at this with the Earth activity yesterday, and we'll talk about it in class some more today. But objects that have the same spin are magnetized. So objects that have the same spin are magnetized. So for instance, if we have an ordinary object, inside of it the electrons have spins that are in all different directions. And in fact, the directions mostly cancel each other out based on their spin up or spin down. And when they cancel each other out, they're non-magnetic. So this one is a non-magnetic material. However, if they all have the same spin, so we'll have them all going towards the right. If they have the same spin, then we have a magnetic material. So this is a magnetic. Dunkin' Donuts tonight. This video is sponsored by Dunkin' Donuts. If you don't just eat, you Dunkaroos. Alright, so this is a magnetic material. Notice the direction of these lines. They're pointing to the right. So if you trace these lines outside of the magnet, they're going to go out and back in. Out and back in. So can we see where the North Pole is and the South Pole of this magnet? Well, we know that field lines go out of the north and into the south. These field lines that are inside the magnet, the red arrows, that's called the magnetic domain. Magnetic domain. And that will say are the field lines inside the magnet. I'm going to write right below it, sorry. Field lines inside the magnet that are due to the alignment of the charges, we'll say of the atoms. I guess electrons. And inside the atom, notice they go from south to north. Or inside the magnet, they go from south to north. And then outside, they go from north to south. So inside, they go from south to north. Now the next question is, well, if it's the spinning of the electrons that cause the magnetic field, in the last unit we talked about the movement of electrons that cause current, is there some sort of relationship between magnetic field and current, or magnetic field and the electric field? We'll look at that next time. If you found this video useful, feel free to like or subscribe so we could get the Tibbetts Physics videos out in public and more than 2 viewers. If not, please don't dislike. And that's it for me tonight. See you later.